Hello, I'm Aaron. This is my final project for Spacecraft Design 2. What I've done here is for a Europa probe instrument, is design a solution involving a 6 degree of freedom robotic arm that's actively stabilized using computer vision in what will eventually be implementing in what's called an active vision framework. As a prototype, I built a 2-axis camera apparatus capable of panning and tilting and implementing TensorFlow to detect objects and then subsequently follow them. So next, I designed a 6 degree of freedom manipulator in Simulink, where I designed the linkage lengths, and here is the diagram here in Simscape multibody. From this, I was able to get system responses to servo inputs, as well as extract things like the Jacobian matrix and such. And this is simply tracing a circle on the ground. Here's its plot of x and y. I then created it in CAD, ensuring everything could be physically 3D printed and assembled without adhesives or screws for simplicity. And then I was able to use SolidWorks motion simulation to get much better simulations of the dynamics of the system. So you can see here a camera is tracing a specimen, and you can see how the arm would put inputs to achieve those dynamics. Finally, we go on to the assembly. So here is the arm system. At its core is a Raspberry Pi, which runs a Python code which calls upon the TensorFlow to process the image data and get location data from the environment. It then communicates with devices over I2C protocol with these blue and green cables to an inertial measurement unit, which gives acceleration and gyroscopic data. And also to this servo driver, which amplifies a PWM signal to allow control of the servos. This then uses the standard servo buses to 6 servos, which make up for the 6 degrees of freedom on the arm, which allow it to freely move within the 6 degrees of freedom, as are specified by the control algorithm running on Python on the Raspberry Pi. And here's a diagram of the electronics. We had a couple issues with testing. The arm had some problems early on in that the motors were actually stalling because they were under too high of load. So to kind of counteract this, we installed some rubber bands to the system to add a balancing force so that they're able to stay suspended and not provide a very large load on the motors, so they can be perfectly extended and still hold just fine, even with the servos off. Another major issue I had involves components failing after being fried by high power. The components weren't able to be replaced in time. Unfortunately, I didn't have time to do that, but we were able to continue testing the dynamics with an Arduino pulse width modulation. So effectively, we had successful testing. Timeline didn't account to replace components. Additionally, the focus kind of drifted from computer vision and towards the 6 degree of freedom platform, as it was a pretty broad project. There's a lot involved with it. So it would take more than 3 months to fully complete. But now that we have a good foundation, we have computer vision, we also have the hardware developed, and both are working independently. Bringing them together is going to be pretty easy. So in the future, we're going to replace the failed components, redesign the robot arms so it can sustain a higher load, and implement a neural net for state prediction to enable adaptive control, bringing in the active vision framework that I mentioned earlier, and then to do that also fully implementing the computer vision with the failed hardware. So thank you for listening to my presentation.